Hello everybody and welcome to today's physics lesson. And today's lesson is going to be on Ampere's law, and more specifically on deriving Ampere's law. And we're going to be deriving the line integral of magnetic field dot product of dl equaling mu naught I enclosed. And this is what we're going to try to find the solution to by deriving it by using some calculus. This is also known as a line integral of magnetic field around a current with an enclosed loop equaling mu naught I enclosed, of course. To start off, we need to know that magnetic field is equal to mu naught over I all over 2 pi r. And this is where magnetic field is in a constant circular symmetrical loop. And to start off, let's draw our wire. This would be our wire. Let us show current going through said wire. And with this wire, we need to create a loop around it, an imaginary loop. Now, this loop really could be anything, maybe a square if you wanted to try that, but for the sake of the calculations and the best way to do it, a symmetrical circle works. Now, let us see if this circle is exactly centered. Yep. Alright. So now with this imaginary circle, the reason this works somewhat the best is because this here is r. This is your radius. And this here also equals r. Because it being a symmetrical circle, the radius would be the same any way from the wire to any point. Any endpoint of that imaginary loop that we've just created. And now, with this imaginary loop, let's talk about which way the magnetic field's going. Because the current is going up, we could just use Ampere's law right-hand rule, or the curl right-hand rule, and we can tell that it goes into the page up here, out of the page over here. So our magnetic field would be going this way over here, and this way on the other side. And now, when we have our magnetic field and r, we can start with writing our line integral of B dot product of dl. Now you see, we need to know what dl is. dl could be any set of essentially infinite spaces on our imaginary loop. For example, dl could be this and this. And this right here, which I just drew a line on, is a dl for B. And dl is going to be in the same direction as B, your magnetic field, which makes it much better for our calculations and is easily the best way to do this and solve for it. And although you don't have to use dl right there, dl could be any infinite amount of spaces along this said imaginary loop we have here. This could be dl. Just all these x's are showing spaces which could be dl, dl, dl. So let's just start with something right now. When our magnetic field and our dl are going in the same direction, theta for that spot, which would be our angle theta, would equal 0. So when theta equals 0 degrees, when B, magnetic field, and our dl are in the same direction, our theta is 0. So let me just rewrite this in a better color. So our line integral of B, magnetic field dot product dl, and now we can see that our B is equal to this up here, mu naught I 2 pi r, as our B is going to be constant everywhere on this imaginary loop. Think about it. If we had B here, this B, and we have this B, our B's are still constant. So our B is going to be mu naught I 2 pi over r, and we can take that outside of our line integral as it is constant. So we can have mu naught 2 pi r over mu naught over 2 pi r equaling to our line integral, or mu naught 2 pi over our line integral of dl. And you're going to be wondering what happened to the dot product, this dot product right here. And I'll tell you what happened to said dot product. The dot product, because both dl and b are both in the same direction, right? Our dot product is just cosine theta. And because we already stated cosine theta is 0 degrees, we could just rewrite that as mu naught I 2 over 2 pi r, line integral of dl, cosine 0 degrees, and cosine 0 degrees equals just 1. So that gives us mu naught I over 2 pi r, line integral of just dl. And now our dl is going to be constant, because if you think about it, dl on any part of this loop, dl right here, 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 is going to be 2 pi r, because think about this loop as a whole. dl is going to be constant throughout said loop. So with dl being, or becoming 2 pi r, we can just take it out of our line integral as it's constant. So we have mu naught 2 pi r times 2 pi r. Now, when you just look at that, we can easily cancel out 2 pi r from the top and bottom. When that's canceled out, what are we left with? Mu naught times I. And what was our initial line integral that we needed to reach? In line integral of b, dot product of dl equals mu naught I enclosed. So what did we solve for here? We started initially with said line integral, and we ended with this. So therefore, we solved that line integral of b, dot product dl equals mu naught I enclosed, because said imaginary circle we have must be enclosed for this to work. So there you are, everyone, and thank you for listening to my explanation.